examining passive filters. We examined transfer function and then we did the filter classification. Now we will be examining the low pass filters. Low pass filters, within this subtitle we are going to define cutoff frequency, proper define, and then we will see low pass filters, RL filters, RC filters. These are the simple filters. Complex filters which has got better filter characteristic will have more number of elements in it. These are a few elements included, simple filter circuits. These filters, that means high degree, high elements included circuits, filter circuits, will be examined in a separate course, not within this course. So we will be examining the RL filters and RC filters. Now let's define this definition relation of the cutoff frequency. The proper definition is the power consumed by the filter, the maximum power consumed by the filter over 2, when the power drops to half of its value. For that value, the corresponding frequency is called cutoff frequency. This frequency also is the same frequency which can be calculated from this formula. This formula tells us the maximum of the transfer function module value over square root of 2 is the value for the cutoff frequency. So from this formula we can calculate the cutoff frequency for each filter. Another way of saying is this. I can show it in a graph like that. So if you see that graph, that is the ideal low pass filter, and this is a few element included low pass filter. Now we are saying that is the maximum value. It could be different from this one, but for this case it is just 1. So that's the maximum value of the transfer function module, which is this, isn't it? So divided to square root of 2, the range is, so the coefficient becomes 0.707. So this is that value. That is the highest value. That is that value. So for that value, the corresponding frequency is called cutoff frequency. So if you want to calculate the cutoff frequency, we've got to use this equation here. So this is the change. This is called amplitude change of the filter characteristic, and this is the angle change. So this angle change, this angle is the angle of this transfer function, and it changes according to the frequency. Now let's examine these filters now. Low pass filter. So there is one inductor and one resistor here connected in serial. If you take the output from the resistor, it becomes a low pass filter. The simplest way of saying that is easy. If omega is equal to 0, this impedance, J omega L impedance, becomes 0. That means short circuit. So the input is going to be the same as the output. So that is the highest value, isn't it? Though you can see the input, exactly the same input at the output. So that means 0 frequency signals pass through this circuit. So that is the highest value. And then if the omega goes infinity, so this becomes open circuit. When it is open circuit, there would be no current passing through. No current passing through means that voltage is equal to 0. So for the highest omega values, this amplitude goes to 0. So our curve becomes like that, and this shows that it is a low pass filter. What is the cutoff frequency? Cutoff frequency is equal omega c equal r over L. We could do this calculation later on. Second group is similar now. This is serial RL circuit, and the output taken out from the resistor. In here there is a RC circuit, and the output is taken from the capacitor. If you take it from the capacitor, that's going to be our transfer function, and this transfer related cutoff frequency is this. Now you see this curve now very similar to the previous one, and this curve tells us this is a low pass filter. So this is the outline of those two low pass filters that we have seen here, and these are the transfer functions and cutoff frequencies. Let's calculate these transfer functions and cutoff frequency in the open board. So let's move to this open board. Here we are. So we're going to calculate now transfer function of this circuit. These are connected in serial. So Vi over R plus SL gives me that current, isn't it? So this is that current. So if you multiply that current with R, we get that V out. So transfer function from this one, V out over Vi, so you're going to move this one to here, is going to be R over SL plus R. If you take the L parenthesis, this one, HS, dash transfer function, is equal R over L over, if you take L parenthesis, you're going to move that L upwards, so it's going to be S plus R over L. So that's the transfer function. Now we are saying the module of the transfer function when S is replaced by j omega gives me the characteristic of this filter. So module of it, H, replace S with j omega and find the module of it. Then R over L is real number, the module is itself, and j omega plus R over L. Module of that. So this is R over L over omega square plus R square L square square root. That is the filter characteristics of this transfer function. So now I can say that what is the highest value of this? So H j omega c module maximum value is equal 1. How we found that is easy. You see here this omega is not included in the numerator but in the denominator. In the denominator, to make this denominator minimal, in physical world the smallest frequency is 0. There would not be a negative frequency in physical world. So the smallest value in the physical world is 0. So this is 0, and this becomes R over L, and this gives you the 1 here. That is the maximum value of the transfer function module. Now, we said R L over square root omega c square cutoff frequency square plus R square L square. My model is going to be equal to maximum value over square root, isn't it? So if you get the square of all these both sides, you're going to end up with maybe write it here, R square L square over omega C square R square L square plus equal 1 over 2. So that gives you 2, drops 1. From that you get omega C is equal R over L. So this is the cutoff frequency that we calculated. That is the transfer function here, and this is the cutoff frequency. Now similarly, if you come to this one, the output is equal V0 is equal Vi over, these are connected in serial, R plus 1 over SC is this current, isn't it? So this is this current. This current is equal to this capacitor current. If I multiply this current with this impedance, I get this voltage, isn't it? V0. So 1 over SC. So that gives me from that V out over Vi is equal HS transfer function, and this is equal 1 over RCS plus 1. If you put this in RC parentheses, then HS become 1 over RC plus S plus 1 over RC. So similarly, this is very similar to this one, isn't it? So you can say that if you do the same procedure here, you're going to end up with a cutoff frequency is equal 1 over RC. Now, up to now what we have done, we analyze a circuit which has got two elements connected in serial and get the output from one of the elements. And we have seen that these functions module changes with respect to frequency gives me a low pass filter. So I know that in general I can say that this circuit is a low pass circuit. So I know the elements, I know from which element I am going to take the output, and also I know how these elements are connected. What I don't know is the element values. So we don't know R and C values, for example. So from that point on, we can use this circuit as a synthesis in the synthesis of filter synthesis, low pass filter synthesis. How we are going to use it? Assume that somebody asks you, I am trying to find a low pass filter which is very low price, and cutoff frequency of this filter is, let's say, 1000 Hertz. So I know I am going to use a circuit like that because I know this is a low pass circuit, and I know the element type. I know also which output I am going to choose. That's capacitor output. And also I know the topology. What I don't know, the element values. So since the cutoff frequency is given to me, that is cutoff frequency. Since this cutoff frequency given to me, I am going to do this now. Omega is equal to PF. This is 6.28, 1000. Then it is 6,000 280 is omega radian second. So 6280 is equal 1 over RC. So I've got an equation and I know two unknowns. It is good news because if I choose one of the element value, I can find the corresponding the other element value according to that equation. So that means the solution is infinite number of solution pairs that I can get. How I am going to use that facility in engineering is easy, because I know the resistor standard resistors values. There are many standard resistor values, but there aren't so many capacitor values, standard values available in the market. So if I choose one of the most available cheapest capacitor value, SC, let's say this is 10 microfarad, then we can calculate the resistor values here. R is 1 over 620 10 microfarad, 10 minus 2 is 9. So that's micro. So that is 10 to the power 4 over 628. So this is 10,000 over 28. So roughly you can say that if it is 500, so it is 20, so it is 2. So it is in the range of 20. So that means if I drop this to 1 microfarad, it's going to be range between very close to 2 kilo. So you can calculate it from here. So what we have done, simplest way of explanation for that. So we have chosen the capacitor value, the cheapest capacitor value. Find out the resistor value. If the resistor value is very low, not very common, let's say 1 ohm. So what you're going to do, increase your capacitor value and get a reasonable resistor value. So among many of these pairs, you can choose one of the best one, optimum pair as the RNC value calculation. So if you choose these element values, you're going to end up with a filter of which cutoff frequency is 1000 or 1 kilohertz. So the next thing here, you could find this characteristic filter characteristics in Pro Tools by using the frequency response. In the frequency response, this red one, the green one here is the transfer function module change, and this red one here is the transfer function angle change with respect to frequency. But this X frequency here is in hertz, not the omega, not the angular frequency, but the real frequency, of which dimension as unit is hertz. In here, that's the transfer function, but the levels are here in decibel. That means 20 times log 10 h j omega module. So it's not seen here. So this x is here, 20 times log 10 module h j transfer function module, so in decibel, isn't it? So definition of decibel values. So that's end of the low pass filters.